Hey everyone, so this is the next unit where we all talk about momentum and impulse. We're going to start off with momentum. Now, for the most part, this entire unit is going to be fairly short. It's going to be about 2 weeks or so, and that's probably going to give us enough time to do a decent amount of practice questions in class. So just be aware of that. Just like with energy, it's actually also another one that is extremely useful for these multi-unit questions. In fact, you're going to be seeing a lot of questions where you'll see conservation of energy turn into conservation of momentum, turn into projectiles, or maybe some sort of dynamics question or something like that. So we'll start off with momentum. Now, this is a word that I noticed that a lot of people tend to use in explanations. A lot of people have probably heard it in medium, they different media like movies and TV shows. You might have even said it a few times in various scenarios, but you may not actually know what it meant. So that's what I want to talk about today: is what does momentum actually mean? The actual definition of momentum is that it's a quantity of motion that an object has, and it's related to its tendency to stay in motion. Now, first, I'll just note that the symbol for momentum is lowercase p. As far as why that is, not too sure. Most likely because the letter m is already used for mass, and that kind of has a play in momentum, and it'd be very confusing. But one thing I want to also point out is that this definition is very similar to the definition for inertia. If you recall, inertia was an object's tendency to resist the change in motion. That if an object was at rest, then the object would remain at rest and would require a decent amount of force. The more inertia an object had, the more force was needed to start that motion. Or if it was already moving, more force was needed to change that motion. Momentum's the same thing, except now it's related in addition to the motion. So instead of it just being a characteristic of the material on hand, it also talks about or takes into account the motion that the object has. A good example is a bullet and a cannonball. A cannonball has a lot more inertia than a bullet, therefore, it requires a lot of force just to change its motion. But if that bullet is moving and the cannonball is at rest, the bullet is going to have a whole lot more momentum and is going to require a lot more force to stop that motion or to even change the motion. Despite the fact that it has a fairly low inertia, its momentum is extremely high. So we can ask ourselves, what are some things that an object would need in order to have a lot of momentum? The first one is that uh, we can already see right there that since it's related very similar to inertia, that the mass of the object has to play a role in momentum. Just like how inertia affects the tendency to change the motion, momentum kind of has a very similar definition. So it only makes sense that an object that has a lot of mass should be harder to move. In addition, based off of our definition, I also gave the description of motion. That the bullet, because it's moving, has more momentum. So those two things are. It's very clear that those have a big part of momentum. That actually leads us to the equation P equals mv. So P is going to be our symbol for momentum. M represents the mass, and V represents the speed. Now the units for momentum is not, there's no derived unit, there's no like shorthand unit for momentum. It's just kilograms times meters per second, or in some cases can be Newton times seconds. Now you'll see some cases where this is going to pop up. I'll mention this in the next video. Uh, Typically, though, the questions that you'll see will use kilogram meters per second strictly for momentum. But if you use Newton seconds, that also works. That's fine. All right, so let's do a few practice questions. So pause the video, work up, and we'll go over in a second. All right, so really quick, we'll just use the equation P equals mv, plug the numbers in for the car, check out our answer. do the same thing for the truck, and we end up getting that the car has 20,000 kilogram meters per second of momentum, and the truck has 100,000 kilogram meters per second. All right, here's the next one. Pause the video, works up, and we'll go over in a second. All right, now if we read the question, it says that it wants the object's kinetic energy. Well, we know the equation for kinetic energy is 1/2 mv squared. Now, in that equation, I require mass and velocity. From the question, I can already see that I have the mass, but I don't have the velocity. So I'm going to look at this number that I have and see, can I get velocity from this? Because this is momentum, I know that I could use the equation P equals mv, plug my numbers in, and I would end up getting that the speed was 3 meters per second. Now that I have this speed, I can then use the kinetic energy equation to get 9 joules. Now, one thing I didn't mention is that, or one thing that's going to be important, really important later on, is the fact that a lot of times what we'll do is if we're looking at a system of objects, multiple cars, like in the first question that we had, or let's say a bunch of molecules inside of a glass container. Sometimes it's not useful just to talk about one object's momentum, but the total momentum of the entire system. So when we do this, what we're going to end up doing is add up all the momentums. So if I want the total momentum of the system, it really is just the momentum of each object added together. Now, the important thing to note, though, is that momentum is a vector. Now, I didn't mention this before, but in the equation, P equals mv, velocity, v stands for velocity and is a vector. Since it's being multiplied by mass, which is a scalar, that means momentum also has to be a vector. This is seen on the AP reference table by the fact that there's a little arrow over the P and the V to note that both of those are vectors and they're going to be pointed in the same direction. So whatever direction the velocity is, that's going to be the direction of the momentum. Very similar to how the direction of force and the direction of acceleration are always in the same direction. All right, here's the next question. Pause the video, work itself, and we'll go over in a second. All right, I'm not going to go over finding the momentums again because it's just from question 1. So instead, what I'll do is we'll take out those momentums from before, and then what I'm going to say is in the same direction, I'm going to add them up. Again, because they're vectors, same direction is adding up. So 100,000 plus 20,000 gets me a total momentum of 120,000 kilogram meters per second. Since they're going when they're going in opposite directions, one of those momentums is negative. It doesn't really matter which one I make negative. I'm just going to make the car negative. So it's going to be 100,000 minus 20,000, which gets me a total momentum of 80,000 kilogram meters per second. Now, this is going to be something that definitely is going to play a major part in the next section of this unit, which is going to be about conservation momentum. So just keep that in mind, that momentum's a vector, and that we do have to pay attention to what direction the velocities are. That way the signs of the momentums are placed properly. And we're just going to leave it at that. I'll save impulse for the next video. If you have any questions, feel free to let me know. Otherwise, good luck. Have a great day.